with chapter 5. Apparently I didn't save my annotations, so sorry about that. They're on the video if you really want to go. You just click through to see the annotations. You don't have to listen to my voice. But now I got to remember where we actually were. So when we were talking yesterday, nobody had questions, right? Questions? No? Okay. Don't forget to bring me your resubmissions for your test tomorrow. That would be great. I did actually finally go through all the activities, so I'll put grades and stuff in the grade book this afternoon. I'm almost caught up. And I will write a activity by tomorrow. So, we did this, we were looking at probability. Yeah? We talked about some basic definitions of probability. We looked at an example of rolling the dice, and all this stuff is gone because I didn't save it apparently. And we were leaving off probability of events. I think we've talked about the intersection and union, yeah? And the complement. And then we were looking at we did these examples, I remember, where we looked at 52 playing cards, parts, blah, blah, blah. Yeah? Yeah? This all seem vaguely familiar? Cool. All right. So we also say two events can be mutually exclusive. The idea behind mutually exclusive, okay, two events are mutually exclusive if they have no outcomes in common. So basically A, B, all right. So if they have no outcomes in common. All right. Another way to write that would be that the probability of A, we don't use that symbol in this class. Oh. And B is equal to 0, right? So there's no overlap. There is no intersection. All right. Mutually exclusive. Can't happen at the same time. All right, so let's look at an example here. All right, so this was a sample that was taken of students in a survey. The researcher was interested in the following events. A was that the student was a full-time student. B, the student is older than 30. C, the student is only taking one course. D, the student has children. E, the student is under 18. Which of these events would necessarily have to be mutually exclusive? B and E. B and E have to be mutually exclusive. And A and C. Why are B and E necessarily mutually exclusive?
You can't be over 30 and under 18.
Not possible. Not possible. How about A and C?
Unless you're taking one 15-credit class, you can't be a full-time student and taking one course.
True. I don't know of any 15-credit classes. Not that I'm aware of. So, all right. Any others? Any others here mutually exclusive? Can you be full-time and over 30? Can you be full-time and have children? Can you be 15 and can you be full-time and be under 18?
Yep.
Sure. Yeah, I think if you go match these other ones up, I think you're going to see that none of the rest of them are necessarily mutually exclusive, right? So they have some. There could be people that are overlap, but those two definitely are examples. Can't happen at the same time. All right, makes sense. So mutually exclusive means basically can't happen at the same time. All right. So something that I've kind of introduced here, right? So typically our events, right? We denote with capital letters. Oh, I guess I said I didn't have a slide for this earlier, and I made a slide for it, and now I actually did have a slide for it. It was just way later than I thought it was going to come. And then we use the probability notation like that, right? I think we already wrote this down. Is that true? Okay. I'm getting everything confused because I'm also doing probability in my 107 class, and I can't remember what we did in which class anymore. All right. Cool. So we already covered that.
Can you go back to that?
Yeah, I think we already did that yesterday though. Yeah, right. This probability notation. Yeah, I think that's actually a duplication of a slide we did earlier. All right, so let's look at. You can calculate probabilities from a table. So this shows the distribution of resident self-identified religion. So this is for you have Protestants, Catholics, Jewish, Mormon, and other. I think these are the. Well, these would just be. Seems like these can't be the top ones, right? Because it seems like there'd be more. I think there's probably more Muslims than Jewish and Mormon people. But anyway, it doesn't matter actually. I was thinking it was the recording of a top one. I don't know where this chart came from, but anyways. All right, so what's the we have these events A and B. So A is that the U.S. resident identifies as either a Protestant or a Catholic, and B is that the U.S. identifies as something other than Catholic. Okay, so looking at these probabilities, what would be the probability of A? So remember, how do we define A? So A is Protestant or Catholic. So what would be Protestant or Catholic? You have these, so Protestant or Catholic. That's going to be the probability of Protestant, right? Plus the probability of identifying as Catholic. Okay. And so you would just say, okay, well that's 0.513 for Protestants, 0.239 for Catholics, and then what would be the sum of those? 752. Yeah. Okay. So about 75% identify as either Protestants or Catholics. Question, are these two events, as far as we know, are these two events mutually exclusive, identifying primarily as Protestant or identifying primarily as Catholic? Yeah, you would think they probably were only allowed to choose one of religion. So notice that these two right here, these are examples of mutually exclusive. So no overlap. And since they're mutually exclusive, that's actually the reason that we can just add their probability. So we can just add these probabilities because there's no chance that anybody is in both groups. There's no overlap here, so we don't have to worry about adding up their probabilities. We're going to see examples later where that's not the case. If groups overlap, it's not so simple. All right? So that would be for Protestant or Catholic. What was the one above that? B is that the U.S. resident identifies as something other than Catholic. So how would you go about identifying people that are identifying as non-Catholics?
Everything but Catholic.
Yeah. So one way to do that would be to take all those, add them all up. So you could take the 51.3% that are Catholics, the 1-something% that identify as Jewish, the something% that identify as Mormons, and the something% that identify as other. And then you add all those up, and what do you get? Probably 0.761 maybe, if you add them all up, if I had to guess. Anybody want to add those up and check it for me? I think that's right. Yeah? How did I know it was going to be 0.761?
You took 1 and subtracted 0.2.
Yeah, notice that the probability of Catholic is 0.239. So then everybody else would just, the total has to be 100% of your population, right? 1.0. So another way that we can calculate these complement events is we can just take the probability and subtract them from 1. So the probability of not Catholic and the probability of Catholic necessarily have to add up to 1. Because if you've taken all the non-Catholics and all the Catholics, you've now covered your entire population. So the probabilities better add up to 1. All right? Cool. Make sense? All right. So this is generally the case. So typically, if you have the probability of A plus the probability of its complement, they necessarily have to add up to 1. Okay? Always has to happen. If they don't add up to 1, that means you missed somebody, because by the time you've covered an event and all of its complement, you've covered everybody. And so another way that we kind of use this sometimes is that the idea is that if you want to calculate the probability of an event, you can just take 1 minus the probability of its complement, and vice versa. So this is always true. So the probability of an event is always 1 minus the probability of its complement. Yeah? Does that seem intuitive? Right? Something has a 25% chance of occurring, it must have a 75% chance of not occurring. Right? They got to add up to 100%. All right. Let's look at an example of perhaps when we might have non-mutually exclusive events. So this is reported by the Census Bureau. 51.4% of the U.S. population is female. 10.4% of the U.S. population has been divorced at least once. And 6% of the U.S. population are females that have been divorced. Calculate the probability that if you randomly select a U.S. citizen, that you get someone that is either female or has been divorced. All right, think about that for a minute. Let's see if you can come up with an answer that you think is reasonable. You can consult with your friend, or you can give, yeah.
Wouldn't they overlap? 10.4%, 6%?
There is some over. That's the tricky thing here, is there is overlap. That's the problem because when if you look at if you think about it as like a Venn diagram, right? Here's women, and here's people. Say divorcees. I think that's a word. I don't know, but people who have been divorced, right? There's overlap. Yeah, it's not necessarily that everybody is exclusive, right? Okay. So think about that and see if you can get a. So these are examples. So in this case, right? Divorced and female are not mutually exclusive, right? There's overlap. So you can ask your neighbor, your friend. You can Google it. See if you can come up with a number that you think is the case.
And 55.8%.
So here's a guess. Okay. Any other guesses?
I'll go with 51.4.
Okay. Anybody else got any guesses? Population, female or divorced? Okay. Any other guesses? So in the last example, all I did was add them up. So why can't I just say the probability of female plus the probability of being divorced? Right? Because that would be what? That would be females are 51.4%. 10.4% of the population has been divorced. So add those up and get 0.618. Why can't I do that?
You'd be counting the 6% twice.
That's the problem. Yeah, because think about this little Venn diagram. If I add up all of the females, yeah, and then I add up all of the divorcees, what have I done? Right here in the middle? I've accounted for the people in the intersection twice, right? So any woman who's been divorced, they got counted with the women, and then they again got counted with the divorcees. And so those women who have been divorced got counted twice. So how can we correct for that error?
Just subtract that number out.
yeah, we're going to take that number out once. So this 6%, right? So that 0.06 was counted twice here, because they got counted with the women and they got counted with the divorcees. So what we do then is we just take it out once. So we take it out once. So then we just take that 0.618, subtract off, those 6% that we counted twice, and that's going to give us 0.558. So that would mean, I think this 55.8 was a good guess. Yeah. Okay. So when you have events that aren't mutually exclusive and you're trying to calculate the probability of one or the other, it's not just as simple as adding the probabilities. You have to take that intersection out, because if you don't, then you've unintentionally accounted for it twice. So you're inflating the number. Okay. So there's actually a formula for that. I'll write it on the next slide. Any questions about that? Why we subtracted it out? Okay. So the idea is, in general, then, right, if you say here's A, right, here's B, and if you take the probability of A plus the probability of B, right, A plus B, well, you've made an error. You've added your intersection twice. So if you take that intersection out once, then that will give you the probability of A or B. So this is the general addition rule. If you want to calculate the probability of A or B, take A plus B and then take the intersection away once. Right? All right. So we're starting to amass some formulas. It only gets more fun, I promise. All right? Okay. Of course, if they're mutually exclusive, we saw this in the example with the table, but it makes it kind of nice, right? If you have mutually exclusive events A and B, right? Well, what's true about the probability of A and B happening at the same time if they're mutually exclusive? What's the probability they'll happen at the same time? It's 0, right? They share nothing in common. What's the probability you get a student that's over 30 and at the same time under 18? 0. It can't happen, right? So if you have mutually exclusive events, then that formula, probability of A plus probability of B minus the probability of A and B, right? This formula, the general addition formula, if you have mutually exclusive, then this right here, it simplifies because the probability of A and B happening at the same time is just 0. So then for mutually exclusive events, you can just add the probabilities together and not worry about the intersection. So you just have to know whether or not you're dealing with mutually exclusive events or not. Whether you can decide if you can use this formula or if you need to subtract out the intersection. Okay? Cool? All right. What does mutually exclusive mean? Am I the only one here? I feel like there's at least 30 of us here. What does mutually exclusive mean? Yeah, don't overlap, can't happen at the same time, right? Okay. What does mutually exclusive mean? Can't happen at the same time. Okay. We're going to have another concept later that's not mutually exclusive, so it's very important that you understand what mutually exclusive means, because I don't want you to get confused later. All right. Cool. All right. We've seen contingency tables now. That came at the end of chapter 4. Contingency tables can help us look at the relationship of how two categorical variables work together, right? Typically, what we have is we have some names for these. So like in here, you good?
Yeah, I finished it.
Okay, so out here, in here in the middle, okay, in here in the middle, these are what we call joint events. And out here on the sides, okay, these are what we call marginal events. Because they're in the marginal, or they're in the margin of the tables. So in here in the joint event, right, these people right here, if we look at the application, this was looking at the relationship between teachers' highest degree and whether or not they plan field trips for their students in rural schools in Tennessee. So these teachers, or these 14 people right here, they were jointly had bachelor's, right, and field trip. So that's why we call it a joint probability or a joint event, because these are people that had two things happen at the same time, right? They did one thing and the other thing jointly. Out here on the margins, though, that's just these 32 people were only the people who did field trips, right? So in the margins, it only tells you something about one event, but in the insides, it's telling you something about people who did qualify in two different events, right? Okay. All right. So I think I got this table on the next one. Yeah, there it is, if you're still trying to copy down. So what's the joint probability that a teacher has a bachelor's degree and they took their students on a field trip? So has a bachelor's degree and took their students on a field trip. What do you think? So we'll say bachelor's degree and field trip. So how many people had a bachelor's degree and went on a field trip? 14? How many people were in this sample? 51? 51. Yeah. So the probability that if you pick so like you got 51 teachers in your sample, the probability that you pick one up and that person has a bachelor's degree and took their kids on a field trip is 14 out of 51. And that's approximately what?
2.7.
About 2.7. So about 27% of these people have bachelor's degrees and took their kids on field trips. What's the marginal probability that a teacher has just a bachelor's degree? So probability of just having a bachelor's degree. So where is that number at? Just a bachelor's degree.
28.
So the bachelor's degree is bachelor's degrees total. So that's over in the margins. That's 28 out of 51. So what's that come out to be, like 55, 56% or so? 0.55-ish. Okay. I think we're going to revisit this example. All right. Any questions on that? Okay, joint just means two events happen at the same time. Margin means it's only looking at one particular event. All right, and you're looking at the totals if you're looking at the marginals. All right. So now I got a question for you here, and now I'm wondering about my slides, but okay. We kind of actually already talked about this. Let's suppose I got two dice up here, and I'm gonna roll them back here. You don't get to see what they're on, right? And I say to you, okay, I just rolled two dice, and the score is going to be the sum of those two dice. And I'd like to know if you would like to bet on the dice coming up as a 7. Okay, and to make it interesting, I'll say, okay, I'll make a bet. If it lands on 7, I'll give you like 10 points back on your exam. But if it doesn't land on 7, then I'm going to take away 5. Or maybe I'm feeling nice. I'll only take away 3. Okay. So if it's a 7, you get 10 back. If it's not a 7, then you lose 3 points, right? So then we'll put that here. So win. If you win, it equals 10 plus points. If you lose, right, then it equals 3 minus points, right? You lose 3 points. You want to play? You want to play? Okay. Anybody who here would play? Huh? Oh, you want to play? For real? I'll go find some dice. Okay.
Get a dice number generator on your phone. a dice
Yeah.
generator.
Yeah. We'll need to get some. Yeah, we could use a simulator, but then who would take that bet? Who would take that bet if I offered it? How many people in this room would take that bet? Okay. You would take it. You take it? No?
What are
Christian
the
would-
chances?
So that's a good question. The question becomes, okay, so before we gamble, we should have a good understanding of what our probability here is, because we stand to lose quite a bit, or to win quite a bit, and not to lose a ton. And this is actually typically how most casino games are set up, right? They give you pretty good odds, so you make like $1 bet, and you think, yeah, maybe I'll lose $1, but hey, I could win 20 or something, right? So if we look at this, what's the probability of actually winning then, right? So what is the probability of A? So we need to go back to that chart we had. Remember that chart with all the 36 outcomes, the two dice? And what was the decision on that as far as the probability of rolling a 7?
Be 6 over 36.
So there were 6 ways to do it. Is that true? Was that what it was? 6? Mm-hmm. And there's 36 possibilities. So you have a 1 in 6 chance, which as a decimal comes out to be 16.6666666. Is that true? Right? So which would be about a 16.7% chance. Right? You want to take the bet? You got a 16.7% chance of earning 10 points, and you have a 83% chance ish of losing 3 points. Still want to take it? You still want to take it? Yeah?
Sure. No.
Oh, and like real life, yeah, I would just take that as only 3 points, but
Yeah. So
if I was thinking strategically, no.
right, but in real life, if it was given to you, a lot of people, I think some chunk of people would, because they think, 3 points, it's not going to kill me, but hey, I get 10 points back. Okay, right? How about money? Would you do it with money? If I started running a casino out of here, and nobody reported me, and I said that a $3 bet, you have to put $3 down. If you put $3 down, you get 10 back. If you get your bet plus 10, you get 10 back if you win. If you lose, you got to pay me $3. Would you take that with money? You do it with money?
Yeah.
So you're willing to lose $3 for the ability to win 10. It's just $3. So dollars are less precious than points on statistics exams. Oh, this is an interesting market I could get myself into. Okay. All right. I like this. Okay. All right. So this is okay. So let's think about it. What if I give you a hint though? Okay. So let's say that same game, same idea, right? So you win, I give you 10 plus points, and if you lose, I give you minus 3 points. But, so I roll the dice, roll them on the ground, I roll them out here, and I don't tell you what it is, but I say, okay, the dice were odd. The dice came up odd. So I'm not going to tell you what number I'm looking at, but they added up to an odd number. Now do you want to take the bet? You know it's an odd number. So it's got to be what? It's got to be a 3 or a 5 or a 7 or a 9 or an 11. You want to take the bet now?
Yeah.
Maybe. What is it? So go back to our little chart here. I'll just draw it here. It doesn't take me that long to duplicate. But you can just scroll back to yours. Because you were smart and you didn't erase yours. Not like me. Now, if I tell you it's odd, what do you automatically get to do?
Subtract all the evens out.
Yeah, we don't even have to worry about all of the even values because I've already told you they didn't occur. Right? Now, so how many options do we actually have to pick from? Yeah, so now notice there's only 18 possible ways that these dice could be sitting right now. And how many ways are there still to win? All 6 ways to win. So now you have a 6 and 18. What is that, a 1 in 3 chance? And so that's about a 33% chance of winning. Now, you want to take the bet?
Still not that big.
It's still not that great. Yeah. So, but by giving you information, what did I do? I gave you a little bit of information, and then what happened to the probability of your winning, though? It increased, right? So I've given you information about an event that occurred. It changes the probability of your event. This is an example of something that we call a conditional probability. Okay. What if I tell you this? What if I tell you the sum of the dice is even? Now you want to take the bet? Why not? Yeah, what's the probability of A if I tell you that? Boom. Don't take that bet. Okay? Don't take that bet, because if I tell you I roll them and I say, hey, the dice are even. You want to bet? Who wants to bet on a 9? 10 points back on your exam. Anybody? Nobody. Don't take that bet, right? It's a probability of 0. So I can give you information that actually changes your probabilities or your perceived probabilities of winning, right? Cool. This idea then is that conditional probability. The whole point here is we're looking at the probability of an event, say A, given. I'll put on parentheses here. Conditional upon, right? So that's why we call it conditional probability. So it's the probability of event A given that an event B has occurred. So the probability of something given something, right? So if I said, what's the if I asked you to estimate, or you're going to randomly select a day in the year, and my question would be, what's the probability that the low temperature was below 40 degrees, right? Well, if you're just talking about a whole year, then that's going to be one probability. But if I say, what's the probability the low temperature was below 40 degrees, given that the day was in October? Does that change your probability of the low being below 40? Sure, it does, because now you've tossed out all the summer months. Okay, so it changes your probability. And there is actually a way we can calculate that. Okay, so let's think about this. We can look at a picture here. This is the definition. So let's go back to our handy Venn diagrams. Here's maybe A. Here's B. Okay. The notation we use for this is we call this the probability of A. Now, if you remember from maybe 94 or one of your algebra classes, the set notation, you list the variable and then the conditions on the variable. We used a vertical line for that, like x such that x is greater than 5 or something like that. So we use the same notation in statistics. So this is the probability of A given B, right? Just like it's written in words right above. Now, if B is given, where in this Venn diagram are we necessarily stuck? So this is the given condition. B is the given condition, which means it has to happen. I'm telling you it happened, or I'm telling you it has to happen. That's the condition, right? I'm telling you the day has to be in October. I'm telling you the number has to be an odd. That's the given condition. So on this Venn diagram, where are we stuck at? We're necessarily stuck where? Could I be out here? Could I be here? Could I be here? No, where do I have to be? I have to be in B, don't I? Right? That's the given condition. You're not allowed to go anywhere outside of that because I'm giving you that. I'm telling you have to pick. I'm telling you the day has to come out of October. So why would you even care about the rest of the year? Forget about the rest of the year. Only look at October, right? I think I need a new slide here. I need a new slide. Didn't leave myself enough room. All right. So let's say. So let me redraw my picture here. So here's A. Here's B. Once I'm given B, right? You can just forget about the rest of the population. I don't care anymore because now you just live here, right? You're stuck there, right? Now remember though, my goal here is to calculate the probability of A given that I'm stuck with B. So in this picture now, where's the only place that A could possibly happen? It's got to be right here, right? So this is the intersection of A and B, and it's the only place that A can occur given B, right? If B has to happen, the only place that A could possibly happen is in the intersection. You know, we can't consider any of this other stuff out here because we're stuck inside B. So then what that does is it gives us a nice way to calculate the formula probability, right? Remember, the probability, the most basic definition is how many ways can it happen divided by all the possibilities. Well, we're stuck in B, so the probability of B is now our new universe because we're stuck in B. And the only place that A can happen is in the intersection. Okay. And so this is a formula that can help us calculate conditional probabilities. All right. So you've got the first formula, which is that general addition rule. That helps you relate the intersection, the or to the and, or the union or to the and. The or and the and relates to those. But this is a different constant. This is now we're talking about, okay, what's the probability of something if you tell me another event's already happened? So we can return back to let's go back to this one, right? This field trip example with the field trips and teachers and blah, blah, blah. Okay, so this was trying to look at whether or not, a teacher's highest degree affected whether or not they would actually plan field trips for their students. So if we look at some probabilities associated with that, let's say, in general, what's the probability that a teacher took their students on a field trip, just in general? So the probability of a field trip. Yeah, so you go look, these 32 people planned a field trip out of the 51 teachers, right? And what does that give you as a probability if you divide that out? 60 something? 63%-ish? Maybe? About 63%? Okay? Yeah? Now, try this though. What's the probability that a teacher took their children on a field trip given that they had a master's degree? Given that they had a master's. So how would I, if maybe F equals field trip and M equals master's, right? How would I denote this? I'm looking at the probability of what given what? M given F or F given M? Yeah, field trip given master's. So I'm looking for the probability of field trip given master's degree. Now there's two ways we can go about this. We could just get this, if we have a nice contingency table, we actually don't need our formula at all. Like notice on this one, for example, how could we figure this out without the contingency table?
Just be 18 divided by
Yeah, so if you look at if it's given master's degrees, I can just lose the rest of my table, right? Because I have to be in this row now, right? The given condition is a master's degree. So I'm just going to toss out all my teachers that have bachelor's degree. I'm not worried about them right now. I'm only looking at masters. And within the master's group, how many went on a field trip? 18. And how many of those were there? 23. So 18 of those 23 teachers took their students on a field trip. What does that come out to be? 0.78. Okay. So what information does this tell us? What is about the relationship between these two variables? Apparently, what can you infer from the comparison of these two probabilities?
The teachers with the masters are more likely to take students on a field trip.
Mm-hmm. The overall probability that a student got to go on a field trip was at 63%. But if you just look at, given that a teacher had a master's degree, those students actually had an increased likelihood of going on a field trip. So it shows that apparently, at least in this sample, it shows that teachers with master's degrees are more likely to schedule field trips. Yeah. Right? So if you tell me if you tell me that this teacher has a master's degree, then I would make maybe an assumption that, then it's probably more likely that their students went on a field trip. All right. And I realized I think I just did something out of order again. So I was going to give you the formula here, but I already gave it to you. So, woohoo. Yeah, I'll just write it again just for good sense. There you go. Okay. And it's important to remember the given condition is always the one that goes downstairs. Okay? So whatever the given condition is, that's the probability you divide by. Because that's your new sample space, basically. All right? We can check this one with the. It's like if we check it. Check the field trip example. Okay. If you do the probability of, say, masters and field trip, right? Then that would be masters and field trip. That would have been 18 out of 51. Go back to your table. Which is approximately what? 35%-ish, 36? 0.35, right? And if you look at the probability of just having a master's degree in general was 23 out of 51. So that's about, what, 45%? 46? 45, right? Then we can check, if we want to look at what's the probability of a field trip given a master's degree. According to the formula, that should be the probability of master's degree and field trip divided by the probability of a master's degree, because that's the given condition, which was the master's and field trip was 0.35. The master's degree alone was 0.45. And if you divide those by each other, what do you get? Somebody do that for me.
0.777777.
So 78? Yeah. So about 0.78. Isn't that what we got here? Yeah. So it works. Okay. Excuse me. Cool. So it's the probability of the intersection divided by the probability of the given condition. That gives you a conditional probability. All right. Any questions about that? No? Feel pretty good about that? All right. Well, let's see where we're going. Let's wait. I want to start this tomorrow because this is going to give us. This will be a good place to pick up tomorrow. But go ahead and get started on your homework. I'll try to remember to actually save these annotations this time. I think I saved them. I just must have forgot to upload them. Bummer.